So I just want to talk teaser, 10-minute quantum algorithms. What are these things? What do they do? Where can I engage with this? What do I do when I see these headlines? Okay, so what can I do with a quantum algorithm? They offer some speed up in some cases, better than known classical methods with a lot of caveats. And I hope to hit on some of those caveats in just one example, but also sort of prime you to think about the assumptions of these methods, what they can do, what they can't do, and where you could possibly look to use them. Okay, cool. They let you, if I were to bias, I would say, efficient simulation. If I was saying, where could a quantum computer help first? You would say, simulating something quantum mechanical, the movement of a molecule, its interaction with its environment. That seems like a great thing, which we know is classically intractable so far. Applications, cryptography, optimization, machine learning. I'm skeptical of some of these applications, like just because I can make a qubit act like a random number generator, that doesn't just make it, a machine learning random quantum thing, But if you had data that was already quantum and you could somehow apply a quantum algorithm to it, that would be a wonderful thing, at least for me, that would inspire me first. Great, so what do you need to engage with this quantum space of methods? Linear algebra, you're gonna be doing matrix manipulation, optimization. Bert hit on a bunch of examples of quantum I would say optimization for quantum and quantum optimization are very different things. Similarly, there's a bunch of, say, classical linear algebra that is needed in quantum. And so I would look for, if I was an applied mathematician looking to engage with this space, places where my skills that already exist map into an existing problem. At least that's what I did. So I study black box, noisy optimization, and I've done this for lots of systems, and quantum has a lot of those. And so think of that in your head, in your research head. Prob and stat, there's a ton of prob stat analysis that needs to happen for these systems. And they know so much about their systems, which is what makes it so exciting to work with the quantum people. Like, they know so much about their problem. It's not just like, oh, here's a black box. It's like, no, it's a black box. The sum of all the outputs should be 1. It's a positive semi-definite thing underlying it, normally distributed with variance that's controllable over the parameter space. And they know so much about their problem. Using that in your method is I think, critical for making inroads. Numerical analysis, of course, proving, analyzing methods. Great. So where can you guys, working applied mathematicians, go? Algorithmic design. Definitely. Error correction, mitigation. Bert hit on a bunch of those. Places where, if you have any of these things in your head, modeling and simulation, verification, benchmarking of methods. There's some great stuff like Torsten Hoffler at ETH. He talks about, just from very much like a classical approach, analyzing quantum methods and when they may or may not succeed in different scenarios. Optimization is needed throughout the quantum stack, from the design of the device, the control of the device, the algorithms that run on the device, the whole communication protocols, the whole stack needs optimization. Great. Okay, so I'm going to give a handful of examples of methods you've maybe heard or algorithms, and I'm going to talk about one, and then I'm going to wrap up. Shor's algorithm, right? Efficient integer factorization. Okay, cool. Under the caveat that you have, tens of thousands of more great qubits, that's definitely needed. So there's always a caveat with all of these, and I want to make sure I know the people who write these algorithms and advocate for these algorithms don't always tell you all the caveats because they're trying to sell their method, which is great. But understanding under what conditions these things work is important, I think, especially for applied mathematicians, to best understand the space. Grover search, I think Grover search is amazing. In expectation, if I wanted to find your name in the list of names of attendees here, in expectation, I'd have to look at n/2 things. I think every applied mathematician is okay saying, I might be the first name he finds, I might be the last name, but in expectation, I should be n/2. If you could somehow get your database of names into a quantum computer and apply Grover's algorithm, it'd be root n/4, approximately, in expectation. Queries of that oracle to find your name. Okay, that to me is amazing, that I can get something less than order n expectation to find something in a list of n things. Now, how do I get my thing in that quantum computer? That is not yet known. Sorry, that is an open question. QAOA is a very attractive quantum algorithm. It's a near-term algorithm that needs sort of limited amount of quantum resources, so it's very interesting. HHL algorithm, it says it can, solve systems of linear equations exponentially faster than classical methods. HHL, the names of the 3 authors. Quantum phase estimation, I guess I'll jump past that. So I'm running out of time, but I just wanted to grab HHL and give some caveats. Before someone says, hey, I can solve a system faster. I can solve AX equals B in time that scales logarithmically with the size of the system. And classical things are usually polynomial. And so you'd be like, whoa, why don't I solve every system this way? Okay, caveats, right? This is only going to generate a quantum state that sort of aligns with the solution. And you need to measure it, so there needs to be some stochasticity involved here. Extracting the full X requires lots of samples of the quantum state that is produced that aligns with the solution. Can your application, leverage the quantum state directly and not, maybe you can do some operations on that before it comes out of the quantum system. And so then it would be especially attractive. And HHL depends heavily on the condition number of A. So do you have a nice A that is sparse, easily encoded on the quantum system, and you only need sort of an X that has, norm 1 aligned with the solution X, quantum state that aligns nicely with the solution vector X. So these are caveats to apply HHL that need to be answered. But yeah, loading the problem device on the, all these other costs are not included. But so these algorithms are often written, let's assume I had my matrix nicely on my quantum system, and my right-hand side was encoded this way. Like, okay, how did that happen? Oh, I had some quantum memory that did that, but okay, this is open problems. So quantum algorithms, very much in their early stages. There's a whole day tomorrow devoted to that, and I'm just here to excite you. You certainly can ask me questions or the other experts about anything I've mentioned here. Applied mathematicians, I think, error correction, optimization, analysis, convergence, all the stuff that we do for other kinds of systems using the quantum space and understanding all the rules of their game. And they know so many rules of their game. It's really great to use and work with the quantum problems. I mean, of course, there's scalability and error correction and efficiency and hardware limitations, and understanding these and designing methods that are hardware aware. It's just one opportunity among, I'd say, hundreds of algorithmic places that applied mathematicians can contribute to the quantum space. So with that, I'll say thanks.